Okay, in order to begin the study of the glycolytic pathway, I'd like to just make sure that everybody is aware that the glycolysis is expressed as in all cells. I like to start out with talking about glycolysis, though, first in red blood cells. Red blood cells have a relatively high ATP requirement because of all the transporters that they express on their cell surface in order to maintain ionic balance and osmolarity. The only form of ATP that they can generate is through glycolysis, of course, since red blood cells do not contain mitochondria. And the mitochondria is where the activity we will see for the TCA cycle and oxidative phosphorylation. So red blood cells on their cell surface will have a unique glucose transporter. And we've seen this transporter before. This one is in particular called GLUT1. Now, because red blood cells have a strong need for glucose at all glucose concentrations in the blood, because glycolysis is the only form of generating energy, the glucose 1 transporter is considered a very high affinity transporter. So what does this mean? Well, if we look at our graph of transporter activity versus substrate concentration, this would be considered in the y-axis glucose transport into the cell, and we're talking, of course, glucose from the blood being transported by the GLUT1 transporter into the cell. If we map the kinetics of this activity, we will see that it's a saturable process, of course, with essentially a Vmax of the transporter activity, and we can measure a Km of this activity. And what we need to consider here is the concentration of glucose in the blood. Now, under normal homeostatic conditions, the fasting glucose levels in the blood are approximately 5.5 millimolar concentration. After a meal that includes a glucose-based diet, this level will rise to somewhere between 7 to 8 millimolar. Now, these concentrations are important when studying the GLUT1 transporter activity because red blood cells need glucose at all times because glycolysis is their only form of generating energy. So whether we are at a higher concentration of glucose in the blood or a physiologically normal fasting levels of glucose levels, the glucose 1 transporter needs to bring glucose into the red blood cell. So, where do these concentrations of glucose fall on the graph here? Well, we can consider this, for example, being 5.5 millimolar, and this being 7.5. Now, what you need to notice here is the activity of the transporter at these concentrations. The VO is very high at these concentrations. So that means under all glucose concentrations in the blood, the glucose 1 transporter is transporting glucose at a very high rate into red blood cells so that they can oxidize the glucose and generate ATP. Also notice that if we become hypoglycemic, and I think we've all experienced this where you get the shakes and the sweats because your blood glucose levels are a bit on the low side, hypoglycemia can be considered, say, approximately around 4 millimolar glucose concentration. Now, where would glucose fit on here when we become hypoglycemic. Again, very high activity of the glucose 1 transporter. So even when we are in a hypoglycemic state, meaning that we have lower than normal glucose, fasting glucose concentrations, the GLUT1 transporter is working just fine. So now there's two phases to glycolysis. The first phase is called the preparative phase. And this phase is essentially preparing the glucose molecule for further oxidative reactions in order to harness and gain that energy in that high-ordered structure. And the preparative phase is going to require the utilization of ATP. Now this sounds a little counterintuitive because glycolysis is supposed to generate ATP, but in the first phase of glycolysis we are preparing the glucose molecule by using 2-ATP. The second phase of glycolysis is called the ATP generating phase. And this is the phase where we are going to harness the energy. We are going to extract the energy. And in this phase here, the end result is that we are going to generate 2 NADH, which are electron carriers, part of our energy currency, and we are going to generate 4 ATP molecules. So glycolysis, when we take our glucose down to pyruvate, which is the last product of glycolysis, the net yield overall is going to be 2 ATP plus 2 NADH per glucose molecule. Now these numbers are important to keep in mind because when we discuss the TCA cycle and oxidative phosphorylation, it will become very apparent that although glycolysis is absolutely necessary for energy generation, glycolysis is a very poor pathway for generating ATP. Per glucose molecule, we are getting very little energy extracted from this higher ordered structure. Okay, so let's begin looking at glycolysis by looking at the first series of reactions that constitute the preparative phase of glycolysis. So, just to reiterate what we said before, glucose in the blood is transported inside the red blood cell by the GLUT1 transporter. Here is glucose. I'm drawing glucose, of course, in the Fischer projection. This is not what it looks like in the cell. It's actually a ring structure, but it's a lot easier to look at glycolysis and the reactions as the Fischer projection will show. So the first reaction in glycolysis is that we have to essentially trap the glucose inside the cell. And the reason for this is because the GLUT1 transporter is reversible. Because it's reversible, that means glucose that enters the cell can exit the cell, and this is not what the red blood cell needs. We need to get this glucose into the cell and begin processing it for glycolysis. So the first reaction that we are going to perform on the glucose to prepare it for these oxidative reactions is the phosphorylation of glucose using ATP to form the molecule glucose 6-phosphate. Now the number of glucose, the carbons are numbered 1, 2, 3, 4, 5, 6. So here we have our number 6 carbon phosphorylated by using ATP. The enzyme that does this reaction is called hexokinase. And again, remember, enzymes that are kinases are going to be using ATP to phosphorylate their substrate. In this case, hexo, because we are phosphorylating a hexose sugar, hexokinase. So this reaction essentially prepares glucose for the subsequent reactions in glycolysis and primarily traps glucose inside the cell. It traps it because glucose 6-phosphate is no longer technically glucose, and so the GLUT1 transporter will not recognize this as a substrate, and therefore it will not transport it out of the cell, giving it a one-way reaction. Now, when we consider regulation here in the glycolytic pathway, the reaction of hexokinase, because it uses ATP, there is a very large negative free energy change of this reaction. So this essentially makes this reaction irreversible. Now keep in mind, chemically, these are reversible reactions, but we are doing biochemistry and biology, and inside the cell, this reaction, because of the large negative free energy change, is considered irreversible. Now, how is this enzyme regulated? Well, this is a feedback regulation at this step. And feedback regulation simply means that the product itself, glucose 6-phosphate, will inhibit the hexokinase enzyme. So as glucose 6-phosphate levels increase concentration in the cell, they will get to a point where they will begin to slow the activity of hexokinase. Why is this important? Well, if there's a problem with building up glycolytic intermediates, we want to slow the process of glucose entering the cycle. And so by inhibiting the hexokinase, we inhibit the glucose to glucose 6-phosphate transformation, and the glucose is fully available to reverse its transport back into the blood, because glucose concentrations building up inside the cell static are not good because of those glycation reactions. So the next step in the reaction, glucose 6-phosphate, is going to be transformed into fructose 6-phosphate. Now this is simply an isomerization reaction, changing the aldehyde functional group into a ketone. Now these functional transformations are done by isomerases because it's an isomerization reaction, and so this is phosphoglucoisomerase. This reaction has a free energy change of approximately 0, and so this reaction is readily reversible depending on substrate and product relationship. So as we take this reaction here, as fructose 6-phosphate concentration increases, potentially it could reverse back into glucose 6-phosphate because of the free energy change, because of the product and substrate relationship. Now, the reason this reaction does not typically, for most cases, reverse is because the product, fructose 6-phosphate here, is kept very low because it becomes the substrate for the next reaction. Therefore, the glucose 6-phosphate, which is the substrate for the phosphoglucoisomerase, maintains a high concentration. And remember our free energy equation, that if you have very low product over high concentration of substrate, take the log of that and you have a negative number because it's less than 1. And that will drive the delta G into the negative range. Now the next reaction is going to be another phosphorylation reaction. And here we are going to be again using ATP as our substrate, our cofactor, and we are going to be generating fructose 1,6-bisphosphate. So essentially what we've done is we've had our 6-phosphate here, and we've added a phosphate on the number 1 carbon. The enzyme that does this is PFK1 for phosphofructokinase 1. Now this particular enzyme we're going to be talking a lot about because this is a major regulation point of glycolysis. I like to call this the gatekeeper of glycolysis. And we will see that this will become the gatekeeper because at this point we can regulate the entire flow of glycolysis. So if this enzyme is allowed to proceed, we can proceed through glycolysis. If it's inhibited, we can reverse these reactions back up to glucose 6-phosphate. And in cells that are going to be storing glucose as glycogen, for example, skeletal muscle, or liver, we can shift the substrates in glycolysis, the intermediates in glycolysis, into alternative pathways. This can also be used for the pentose phosphate pathway. It happens in all cells, primarily in the liver, and here we are going to be generating the biosynthetic reducing power called NADPH, and we'll get to that when we talk about the liver. So how is PFK1 regulated? The regulation of this enzyme in most cells, especially in the liver, is very, very complex. But suffice it to say, initially, we're going to talk about intra-pathway regulation, which is just simply the regulation of glycolysis based on the products that are being made. And this enzyme, PFK1, is regulated by essentially ATP to ADP ratios. So as the concentration of ATP increases, this will inhibit PFK1. It inhibits it because we want to slow glycolysis down. If we have sufficient ATP, there's no use in going through the subsequent steps. Now, as the concentration of ADP increases, the concentration essentially of ATP will decrease with ADP increasing, and so that will relieve the inhibition. The other factor here we need to consider is that the concentration of AMP appears, it increases with extra activity, and this will be an allosteric activator of PFK1. So how does AMP come about? Well, as ADP concentrations rise, we will reach a concentration that will surpass the Km of a particular enzyme called adenylate kinase. The job of this enzyme is to try its best to restore ATP in the absence of large amounts of ATP synthesis, which will come when we relieve the block on PFK1. So this enzyme, adenylate kinase, takes ADP, 2 of them, and converts this to ATP plus AMP. Essentially, this enzyme takes one of the high-energy phosphates from ADP, transfers it to the other ADP, generating these 2 products. The ATP, of course, can go on to be used for energy needs, and the AMP becomes an allosteric regulator. The appearance of AMP is now a positive regulator telling PFK1 to get in gear and start its activity. Now, once we have our fructose 1,6-bisphosphate generated, we have one more reaction in the preparative phase, and this enzyme is called aldolase. This enzyme simply cleaves the fructose 1,6-bisphosphate in between the two 3-carbon units, generating two products. One is called DHAP for dihydroxy acetone phosphate. This name comes from the fact that we essentially have a glycerol backbone with a ketone in the middle, so this is therefore structured as an acetone structure. At the ends of the molecule, we have essentially hydroxyl groups, dihydroxyacetone phosphate, meaning that one of the hydroxyl groups has been phosphorylated. The other compound is glyceraldehyde 3-phosphate. Again, glyceraldehyde, glycerol backbone. We have an aldehyde structure at the number 1 carbon, and we have a phosphate on the 1 to number 3 carbon, giving us glyceraldehyde 3-phosphate. Now, these two products will be entering the ATP generating phase of glycolysis. Essentially, we are going to be talking about glyceraldehyde 3-phosphate, which is the product that moves into the reaction, and therefore the DHAP that's created by the aldolase reaction, we need to convert into glyceraldehyde 3-phosphate. Now notice this is simply DHAP from glyceraldehyde 3-phosphate. This is an isomer. So we are going to do an isomerization to convert this ketone structure into the aldehyde structure. And this enzyme is called triose because we have a triose sugar molecule isomerase. This enzyme, along with aldolase, both of these are readily reversible reactions. Okay, so now let's conclude looking at the reactions in glycolysis by focusing on the ATP generating phase of the pathway. So we are going to be picking up with glyceraldehyde 3-phosphate. And remember, again, this was generated from the aldolase reaction and then the isomerization of DHAP into glyceraldehyde 3-phosphate. So now remember, we have from this point on 2 trioses moving through in parallel in this pathway. So all of the ATP and NADH that will be generated multiplied by 2 from this diagram. So the first step is we are going to perform a complex reaction by a very complex enzyme called glyceraldehyde 3-phosphate dehydrogenase. This reaction is a redox reaction. Now, from chemistry, recall that redox reactions are reduction oxidation, which means that in order to balance these reactions, one substrate is being oxidized, which means electrons are being removed from the substrate. Another must receive the electrons, and that one is being reduced. So in this case, we are focusing on the glyceraldehyde 3-phosphate residue, and we are going to extract these 2 electrons that constitute the bond between the hydrogen and the carbon in the aldehyde group. Now, that means we need an electron acceptor, and in this case, it is going to be NADH, nicotinamide adenine dinucleotide, and we are going to reduce this by giving it electrons into NADH plus a proton. These electrons are what we are oxidizing to remove from glucose, and this is going to be the generating force for ATP and energy production as we progress. Now also notice that there is a phosphate group added into this reaction. And this compound, this product we're generating, is 1,3-phosphoglycerate. So not only are we performing a redox reaction, but we are also adding a phosphate group to the number 1 carbon. This reaction is not using ATP. Rather, we are adding inorganic phosphate. Hence why I said the glyceraldehyde 3-phosphate dehydrogenase enzyme is very complex. It's performing multiple reactions sequentially in the active site in order to generate the 1,3-phosphoglycerate, which has this phosphate addition and has been oxidized, transferring the electrons to NAD to form NADH. This reaction, if we couple these reactions with the next reaction, the delta G is essentially 0. And so these reactions combined are essentially reversible. So now the next reaction is going to be one of our energy harvesting reactions. So in this reaction, we are going to undergo a substrate level phosphorylation of ADP to form ATP. The enzyme that performs this, as you can imagine, is a kinase, and it's called phosphoglycerate kinase because it is phosphorylating a substrate level phosphorylation. Now this phosphate turns out to be a very good leaving group because remember your chemistry here is that we have resonance between these oxygens and making this bond weak so that this is a good leaving group, essentially giving us a high energy nature. So the transfer of the energy from this goes on to ADP to give us our high energy phosphate bond of ATP. When we do this reaction, we generate 3-phosphoglycerate. Now the next two reactions are simply preparing the molecule for a higher energy state in order to generate our second and final ATP. So notice the difference here. We have a phosphate group on the number 3 carbon. This structure, we have the phosphate on the number 2 carbon. So that makes this molecule 2-phosphoglycerate. Now in this case, we have not an isomerization reaction, but simply moving a functional group, this phosphate group, from the number 2 carbon, from number 3 to number 2 carbon. So the enzyme class of this is still part of the isomerase family, but it's called a mutase. And a mutase, generally in our reaction schemes we'll be talking about, move a phosphate group from one carbon to another. In this case, the enzyme is called phosphoglycerate mutase. Now the next reaction here is going to be, again, another preparative reaction to prepare the molecule for our final ATP production. But notice this bond here of the phosphate group. This is not a high energy bond. This is a rather stable bond. So the next reaction, which is done by an enzyme called enolase, is going to generate a structure that makes this bond a high energy bond and makes the phosphate group a better leaving group than it is in the 2-phosphoglycerate structure. And so what we are doing here is essentially introducing a double bond between the number 2 and 3 carbon by removing water. So we are essentially removing this hydrogen, this hydroxyl group, to form water, and collapsing the electrons in to form a double bond. This structure is called phosphoenol pyruvate. And what we've essentially done here is notice we have resonance between the double bond between the carbon and the phosphate linkage with the carbon, and that gives it a good leaving group and a weak bond, so that now we can generate our ATP with this good leaving group. The phosphoglycerate mutase, the enolase reaction, these are all reversible. So all of the reactions since PFK1 have been fully reversible, and this will become very important to us as we get into the liver down the road and talk about gluconeogenesis. Now the final reaction here is to harvest the high energy from this phosphate, and in doing so we are going to do a substrate level phosphorylation of ADP to create ATP, and again, because it's a phosphorylation, this is a kinase. This enzyme is called pyruvate kinase. And by extracting this phosphate, you'll notice that we have our final product of glycolysis, which is called pyruvate. Pyruvate we will pick up in two different manners we'll talk about in a second. But the pyruvate kinase reaction here, this is essentially another irreversible reaction. This enzyme has an interesting regulation level, and that has to do with the regulation of being called a feed-forward regulation. Recall the product of PFK1. Back in the preparative phase of glycolysis, this enzyme is converting fructose 6-phosphate into fructose 1,6-bisphosphate. This product of the PFK1 reaction, of course, is a substrate for aldolase, but it's also an allosteric activator of pyruvate kinase. Now, why is this important? Well, picture yourself in a line, and the person at the front of the line is dialing, and you have substrate and product moving through your line. Well, you want to just put out a regulator down the way to tell pyruvate kinase to get in gear, become activated, so that there's no backup of substrate and product during glycolysis. Remember, PFK1 is essentially the committed step into glycolysis, the gatekeeper, and all of the reactions after that point are reversible. Since they are reversible, if there's any backup, any inhibition or slowing of the process, these products can back up and cause reversible reactions which are undesirable. And so by the product of PFK1, allosterically activating pyruvate kinase, that makes sure that the downstream enzyme is not a rate-limiting enzyme. Now, in the red blood cell, we have one more step because pyruvate is an acid. And essentially in a red blood cell, if we just stick with these reactions, we have a problem that pyruvate will build up inside the cell and significantly drop the pH because it's an acid. And it's also a metabolic waste product for the red blood cell. Now, in cells with a mitochondria, we will see that this will enter the mitochondria, and in doing so, will be generating product to enter the TCA cycle. But red blood cells do not have mitochondria, so they need to deal with this pyruvate. Now, very important up here is this NADH. Notice the glyceraldehyde 3-phosphate dehydrogenase reaction. we have NAD being converted to NADH in this redox reaction. Well, in order for more glycolysis to occur, we need to convert NADH back to NAD to continue the redox reactions. That means we have to perform a redox reaction on NADH, and we are going to do that with pyruvate. Essentially, what we are doing is converting NADH to NAD+, which will allow us to continue glycolysis. And in doing so, we are going to generate a structure that looks like this. This structure will be very familiar to everybody. We've all experienced this. Essentially, what we've done is we've oxidized NADH, we've removed these electrons, we've added them to the ketone group to generate an alcohol. This is called lactate. I think we've all experienced lactic acid buildup in our muscles. We'll talk about this when we get to skeletal muscle. The enzyme that does this, of course, is a dehydrogenase. In this case, it is lactate dehydrogenase. So this allows the regeneration of NAD so that the glyceraldehyde 3-phosphate dehydrogenase doesn't get depleted of its cofactor, and it also allows the conversion of pyruvate to lactate. Lactate is secreted from the red blood cells into the blood. From the blood, we'll talk about this later when we get to gluconeogenesis. The liver will take up the lactate, and the liver, using the same enzyme, lactate dehydrogenase in the liver cell, will convert it to pyruvate. Then the liver will take the pyruvate, process it, get it into the mitochondria, and then use that product for other essential reactions that we'll talk about later.